To power the electric future, we first must harvest the raw materials buried deep within the Earth's crust.
Heavy machinery breaks down the ore body, liberating the lithium trapped inside the hard rock formation.
Each load represents tons of potential energy, destined for processing into battery-grade materials.
The raw ore begins its journey out of the mine, heading toward the initial stage of size reduction. At the primary crusher, the large boulders are mechanically reduced into manageable chunks.
This brutal mechanical process is essential to expose the valuable lithium minerals for chemical extraction later.
Miles of conveyor belts provide efficient, continuous transport from the mine face to the processing facilities.
Screening ensures only material of the correct size moves forward, returning oversized pieces for recrushing. The crushed ore is accumulated in vast stockpiles, ready for transport to the chemical refinery.
Once processed into a concentrate, the material is loaded into sealed trailers to prevent loss and contamination during transport. The journey from the remote extraction site to the manufacturing hub begins, bridging the gap between raw earth and advanced technology.
Specialized logistics networks ensure a steady stream of raw materials keeps pace with the demanding production schedules of the gigafactories.
As the convoy nears the processing facility, the environment shifts from rugged isolation to organized industrial precision.
Manifest for review, please.
Yes, here it is.
Everything seems to be in order. You may proceed.
Every shipment is weighed with precision to track inventory and verify the quantity of raw lithium entering the refinement stream. Upon arrival, the logistics phase ends, and the material is handed over to the processing teams. With the paperwork signed, the raw lithium is officially transferred into the custody of the battery manufacturing plant.
Gravity feeds the raw lithium concentrate into the facility's subterranean intake system, beginning the refining process.
These silos act as the facility's lungs, holding enough raw material to keep the production lines running continuously.
This is the modern gigafactory, a marvel of engineering designed to optimize every inch of flow and efficiency.
Hundreds of skilled technicians and engineers arrive for each shift, the human intelligence behind the automation.
Security and safety protocols are rigid. Access to the production floor is strictly controlled.
Contamination is the enemy of battery chemistry. Operators must adhere to strict cleanroom protocols before entering.
High-velocity air showers remove even microscopic particles that could cause a short circuit in a finished cell.
Here, raw chemistry meets precision engineering, orchestrated by a seamless blend of human oversight and robotics.
We begin at the mixing station, where the dry lithium concentrate is prepared for its chemical transformation.
Before it can become a battery, the crystalline structure of the material must be altered through intense thermal processing.
Inside this rotating furnace, temperatures reaching 1,000 degrees Celsius convert the mineral into a reactive state.
The roasted ore is pulverized into a microscopic powder, increasing its surface area for chemical treatment.
Filtration acts as a critical sorting stage, isolating the lithium-rich liquid from the solid impurities.
Sulfuric acid dissolves the lithium, separating the valuable metal from the waste rock in a process called leaching.
Filtration acts as a critical sorting stage, isolating the lithium-rich liquid from the solid impurities. Trace contaminants like magnesium and calcium are stripped away at the molecular level to ensure high purity.
Through evaporation, the liquid transforms into solid, high-purity lithium salts, the heart of the battery cell.
Centrifugal force separates the final moisture, leaving behind a damp, battery-grade chemical cake. The particles are micronized to a precise size, ensuring uniform chemical reactions within the battery.
The purified lithium is combined with solvents, binders, and conductive additives to create the cathode slurry.
High-pressure pumps transport the electrode slurry to the coating line without introducing a single bubble of air. The slot die coater applies the active material onto aluminum foil with a thickness tolerance less than a fraction of a hair.
Inside the drying tunnel, solvents are evaporated and recovered, leaving behind a solid, dry electrode coating.
Advanced recovery systems capture 99% of the toxic solvents, recycling them for use in the next batch.
The calendaring process compresses the electrode to the exact density required, maximizing the energy storage capacity.
Automated X-ray or beta ray gauges measure thickness continuously, adjusting the rollers automatically if a deviation is detected.
The wide electrode sheet is slit into narrow strips, sized perfectly for the specific battery cell format being produced. These finished electrode rolls are the fundamental building blocks, now ready for assembly into individual cells. The electrodes enter the dry room, where humidity is kept below 1% to prevent the lithium from reacting with moisture in the air.
Here, the anode, cathode, and separator are aligned with sub-millimeter precision, ready to be wound together.
Ultrasonic welding attaches the conductive tabs that will eventually connect the battery's internal chemistry to the outside world. In a fraction of a second, the layers are wound into a jelly roll, creating a massive surface area within a compact cylinder. Automated taping secures the structure, ensuring the delicate layers maintain their alignment during the casing process. Meanwhile, nickel-plated steel shells arrive, ready to house the fragile electrochemical core. The jelly roll is inserted into the casing, a critical step where physical damage to the electrodes must be avoided at all costs. An internal weld connects the negative anode to the steel casing, making the entire can on the negative terminal. Grooving creates a shelf for the top cap to sit on, preparing the cell for its final seal. Once dried, the cells are transferred immediately to the most critical isolation zone, the electrolyte filling chamber. Precision nozzles inject the electrolyte, a conductive liquid that allows ions to flow between the cathode and anode. Vacuum cycling forces the electrolyte deep into the microscopic pores of the electrode material, ensuring full saturation. The top cap, containing the safety vent and positive terminal, is positioned for the final closure. Crimping permanently seals the cell, locking the chemistry inside a robust steel pressure vessel. The exterior is ruthlessly cleaned to remove any trace of electrolyte, which could cause corrosion or electrical faults.
Every single cell receives a permanent laser ID, linking it to its production data for its entire life cycle.
The cells are loaded into massive formation towers, where they will be charged for the very first time.
This first charge, known as formation, awakens the battery, creating a protective layer on the internal electrodes. The cells are then stored in a temperature-controlled warehouse for weeks, aging to ensure the voltage remains perfectly stable. After weeks of aging, the cells are retrieved to verify they have held their charge without self-discharging. The OCV tester measures voltage to the third decimal place, rejecting any cell that shows even a hint of instability.
Before assembly, the terminals are laser cleaned to guarantee zero resistance in the final weld. Cells are sorted by capacity. Only identical twins are paired together to maximize the lifespan of the battery pack.
We now transition to module assembly, beginning with the application of thermal conductive adhesive to cool the cells.
Robots populate the modules, seating the cells in a precise grid that balances structural rigidity with thermal management. A final optical check confirms the polarity of every single cell before the electrical bus bars are installed. The bus bar is the highway for electrons, connecting hundreds of individual cells into a single powerful voltage source.
High-power lasers fuse the metals instantly, creating a bond that is stronger than the materials themselves.
Every weld is scrutinized in 3D, A single weak connection could compromise the entire electric vehicle.
The high potential test stresses the insulation with thousands of volts, ensuring there is no electrical leakage to the casing.
The battery management system is the brain of the unit, monitoring voltage, temperature, and current in real time. While production continues, random samples are sent to the destruction lab to test the limits of safety and durability.
Vibration testing simulates a lifetime of potholes and rough terrain. Thermal shock tests subject the pack to extreme freezing and scorching heat.
In the crush test, the structure must absorb immense impact forces without catching fire or exploding.
The nail penetration test is the ultimate safety standard, simulating a catastrophic internal short circuit.
At the molecular level, engineers verify that the internal structure remains intact, even after rigorous stress testing.
With the sample batch certified safe by the lab, the main production run is cleared for final pack assembly.
Now verified and tested, the individual modules are ready to be united into the vehicle's structural battery pack.
The foundation of the pack is prepared with a thermal interface layer that will wick heat away from the modules during rapid charging. Heavy lift automation places the modules, while skilled technicians install the complex high-voltage architecture.
Thick copper cabling connects the modules in series, building the voltage up to the 400 or 800 volts required to drive the vehicle.
The pack is sealed tight, protecting the high-voltage components from water, dust, and road debris for the life of the car. Helium detectors ensure the seal is perfect. Even a microscopic leak could allow moisture to destroy the battery over time.
Each finished pack is certified, labeled, and tracked, ready to power a specific vehicle somewhere in the world.
This inventory represents gigawatt hours of stored energy, waiting to replace millions of gallons of gasoline.
From the mine to the module, thousands of steps have culminated in this final shipment to the vehicle assembly plant.
The cycle is complete. Raw earth has been transmuted into clean power, ready to drive the next generation of transportation.
And this is how modern factories produce EV batteries from start to finish.